Okay.
Okay, hello everyone. It's my great honor to have Professor Yuan Chen from Peking University to give us a talk. His title is a generalized spin statistical theorem for loop excitations as well.
Yeah, thank you for the introduction. And so today I will focus on the spin statistics theorem for loop excitation. So I have played my slide for a few minutes. So yeah, so this animation is pretty important. So do you have any idea which metaphor this is? Is it? Yeah, okay, so I will explain it later. So basically, this is the two perpendicular Mobius strips. So when we try to prove two Mobius strips, it becomes the Klein bottle. And yeah, so Klein bottle will be a very important metaphor for the loop excitation. So before I go to any technical discussion, I want to make some analysis. So in the high school or junior high school, the first way to learn about gravity is from Newton's gravity. So we know if two particles have mass, so they have some attractive force is inverse proportional to their distance squared. Yeah. So this is our first understanding toward how gravity works. But the modern point of view is given by Einstein. So in his general relativity, he said that the reason why these two particles or two spheres they are attractive to each other is because the mass causes the curved spacetime. So based on the spacetime curvature, they need to follow some geodesics in the spacetime. So due to this reason, these two spheres they attract each other. Yeah. So I will try to recognize the left-hand side as a property of a phenomena. This is based on our observation of the real world. For example, in our solar system. So based on how this Earth and Sun, how do they rotate with each other, we can kind of conclude they have this force law inverse proportional to their distance squared. And the right-hand side, the Einstein description is much more fundamental. It helps us to get a deeper understanding of this phenomena. Okay, so today I will focus on a slightly different perspective. So it's about quantum mechanics. So when we first learn quantum mechanics in our maybe undergrad class, we know the particle has two types of statistics. So if we try to exchange the position of two particles, we either get plus sign or minus sign. The plus sign means the particle is boson, and the minus sign means it's a fermionic. Yeah, so we kind of just take it for given. This is come from the reason the quantum state, the phase vector is kind of not detectable. So when we try to move the system into its original configuration, they can change up to some sign or phase vector. Yeah, and today I will try to give you a more fundamental description to explain this phenomenon. So why there's a boson or fermion, and then we can generalize to the loop excitation. Okay, so as an exercise, we just focus on the statistics of particles. So everyone is kind of sort of familiar with the definition. Yeah. So when we talk about fermion, sometimes we use two different ways to describe this property. The first one is when we try to rotate the particle by 2 pi, it gives a minus sign. And the second description is when we try to exchange the position of two fermions, we get a minus sign. Yeah. So these two are not coincident. Actually, one applies the other. So this is called a spin statistics theorem. So the 2 pi rotation is called a spin of a particle, and the exchange statistic is defined in by exchange their position. Yeah. So there's a very nice way to visualize why the spin and statistic must be locked with each other. So consider this ribbon diagram. So as a particle in the space-time picture, the particle becomes the worldline. But due to the quantum mechanics property, we know for each particle, they must have some spin. So we can imagine, so say a particle at this time, it has some a little angle, is the direction attached to the particle. So this is called a framing. So when the particle moves in a space-time, it actually forms a ribbon instead of a line. Yeah. So you can interpret the left-hand side as when a particle moves in a time direction, it undergoes this 2 pi rotation. So you can see this ribbon is twisted by 2 pi along this direction. So you can play around this ribbon. So you can prepare the ribbon in this shape, and then you stretch this ribbon, and you can see this configuration can be deformed to this configuration smoothly. Yeah. So this is nothing deep. It's just some topology. You can play around with it. You just make a very long paper and you just stretch it. You can see this diagram is equivalent to this one. Okay. Now let me try to complete this wall line into a circle. So consider, so I put this ribbon as here, and I connect the top and bottom by another ribbon, which is untwisted. And similarly, I can try to connect this one, this top point and the bottom point to become this diagram. Okay, so we know from the ribbon perspective, these two configurations, they are the same, but we can give them two different physical interpretations. So let's just focus on the right-hand side. So let's consider the vertical is a time direction. So at the negative time, I have no particle in the system. And at these 2 points, I create 2 particles, say particle here and antiparticle here. So as time goes, this particle is undergo 2 pi rotation, is a spin, and then annihilate with this is antiparticle. So the left figure corresponds to the 2 pi rotation of a particle. And now let's try to see what happens in the right-hand side. So similarly, in the negative time, we have no particle excitation, and at this point, I create 2 pairs of particle and antiparticle. Say this is my particle, this is my antiparticle, and this is my particle and antiparticle. And now I exchange the position of these 2 particles. So this particle goes to the left, and this particle goes to the right. And we can see finally they annihilate with their partner, the antiparticle. So the right-hand side corresponds to the process. You exchange 2 particles and annihilate with the antiparticle. So although the ribbon, they are always the same. They have the same topology. You can deform one to the other smoothly, but they give a different physical perspective. One is about the spin, and one is about the statistics. Yeah. So I think this is the easiest way to understand why the spin and the statistics must be the same as each other. Yeah. So here I use the fermion as an example. For fermion, these both of them are -1. And in 2 dimensions, we can actually have the anion. So in the 2 + 1D system, when we have some anion, which means this sign can be any U1 phase vector. But for today's talk, I just focus on the boson fermion, where it's easier, and in the higher dimension, there's no anion. Okay, now let me describe operational. Any questions? So this ribbon diagram works for any dimension, but there's some slightly different between 2 + 1D and 3 + 1D. So in the 2 + 1D, if you twist the ribbon by 2 pi, 4 pi, 6 pi, they are all different topology. But in 3D or higher, if you twist the ribbon by 4 pi, it's actually equivalent to an untwisted ribbon. So you can play around. So in the 3D, you can see the line above and the line below. They cannot cross each other. So either this line here or there, they are kind of different. But in 3D or higher, so in the 3D, which means we have the 4D spacetime, these two lines can cross each other by additional dimension. Yeah. Now, if you are mathematician, this is related to the fact the pi1 of SO2 is Z. The pi1 of SO3 is Z2. The fundamental group of SON change from n equal to 2 to 3. If the n is greater than 3, the fundamental group is always Z2. Okay, now let's try to give you some operational way to detect the anion statistics or photon fermion. Yeah. So I call this a T-junction process because usually you draw it as some junction, like it's a T shape, but I put a junction this way. So let's consider the configuration like here. I have a particle 1 and the red particle and blue particle. So they actually are identical particle, but I just show you a different color to demonstrate. So consider initial state, I put 2 particles here. And now I move this red particle into the middle and into the bottom right. And later I move this blue particle from the 3 to 0 and to 1. And finally, I move this red particle back to 0 and back to 3. So you can see, compare the original configuration and the final configuration, the position of these 2 particles, they kind of exchange. So we expect if we apply this unitary operator, I forget to say. So we assume there is some unitary operator which can move the particle along this blue line. So for example, this U1 is some unitary operator, move the particle from 1 to 0, and U3 is the particle, some operator move the particle from 3 to 0. Yeah. So we can apply 6 unitary operators to detect the statistic of particle. Yeah. I want to make a remark. So this process is very carefully designed. This is because if you just try to arbitrarily move 2 particles, then my particle A and B here, you move this here and you move this there. So if you just do arbitrary process, this sometimes may accumulate some dynamical phase. So you want to design a process. For example, there's U1 here and there's U1 inverse here. So U1 means you move a particle from 1 to 0 like this. And the U1 minus means you have the inverse process from 0 to 1. So this guarantees all dynamical phase cancel out under this process. Yeah. Okay, so how do we connect this exchange to previous ribbon diagram? Because when we try to work with particle on the lattice, we don't specify the framing. Yeah, but I want to emphasize we can choose the framing arbitrarily. For example, let's just try to put some black state here. And when I try to move the particle from here to here, for example, the first 2 steps is U1 times U2 inverse. Is actually you move the particle here from 1 to 0, 0 to 2. And you can draw the worldline. Maybe I should call it world ribbon like this. And similarly, you can decompose the other 2 processes into this ribbon and the final 2 processes as this 2 ribbon. And when you try to connect all of these 3 ribbons into this process, you can spend some time to figure out the detail. You need to be careful because we need to specify the time direction. So which ribbon is on top of the other one is important. If you do it carefully, you can see this T-junction process produce the same ribbon diagram I just introduced in the next slide. Yeah, the detail here is not important. I just try to emphasize this process is some microscopic definition of the boson or fermion statistic for particles. Okay, so now let me try to make a more mathematical definition for fermion. So let's consider the fermion can move along the space. And now I have emphasized before, for each particle, it has some spin. So which means there's some small error attached to the particle at each point. And now I enforce the condition that the direction of spin need to follow certain vector field, which means when I try to move the fermion say, along this red circle, I require my spin to always be agree with this the background arrow here. Yeah. So you can see in this process, this blue arrow will have a 2-pi rotation. So we expect if we move a particle around this red circle, we get a minus sign. And so we can notice that if this arrow is always pointing inward, there must be some singularity at the origin. So which means we cannot define this vector field smoothly and non-vanishingly around the whole space. There must be some singularity point. So this singularity is called a second Stiefel-Whitney class. So it's a very well-known and well-studied topological characteristic class of any given manifold. Okay, so we can give a more formal mathematical definition for the fermion. So when we say a particle is fermion, it's defined in the following way. So if we try to move the particle around a closed loop, and it will give you some minus sign. The minus sign depends on the W2, the second Stiefel-Whitney class, evaluate inside this loop. Any question? Yeah. So here I will treat this as a definition, and the previous property follow from this definition. Okay, so here is just some technical detail. So how do we look here? We assume it's some continuous field and the particle can move around. But on the lattice, we can always choose some way to define a vector field. So first, for any triangulation, we can do the barycentric division. And for this barycentric division, we can define the corresponding flow of the vector field on the triangulation. Yeah, so this is just some technical detail, but I want to emphasize the definition works for discrete triangulation too. Okay, now let me give you a quick review, a quick introduction of a Stiefel-Whitney case. I think at least for me, the easiest way to understand Stiefel-Whitney case is some abstraction. If you are a physicist, I think you are more familiar with the Chen case, because when we study the quantum Hall effect, we say the Hall conductance is proportional to the Chen number of your band structure in the first Brillouin zone. Yeah. So we say we have non-trivial Chen number. This means the wave function cannot shoot smoothly in the Brillouin zone. We need to choose a different case to have the non-trivial Chen number. Yeah. So the Chen number, the Chen case is some abstraction to have some smooth vector bundle. Yeah. And similarly, you can think of the Stiefel-Whitney class is the real version of the Chen class. You have the Chen class, it is defined for the complex bundle, and the Stiefel-Whitney class is for the real bundle. Yeah. So for arbitrary Stiefel-Whitney class, WK is an abstraction of n minus k plus 1 everywhere linear independent section of the tangent bundle. Yeah. So let me give you a very quick example. So if we just choose W1 here, according to my definition here, the W1 is an abstraction to n linear independent section of the tangent bundle of an n-dimensional manifold. So which means it's the orientation. So if the W1 is not equal to 0, there's no orientation assignment for the n-dimensional manifold. Yeah, so W1 corresponds to orientable or non-orientable. And also, the W2 also appear quite frequently in the physics context. When we try to define a fermion, for example, on the quantum field theory, we need to require the underlying manifold to be the spin manifold. By definition, the spin manifold means W2 equal to 0. So we need to require the W2 equal to 0, so we can define certain the spin factor, so we can put the Dirac fermion onto the manifold. Yeah. So this is just some review of the Stiefel-Whitney pair. Yeah, I hope it's kind of clear. Okay, so we have discussed the theory of particles, and now let's go to the loop excitation. So there are actually many studies before about the loop excitation. So actually, this paper by Chen and Michael Levin just received the Frontier of Science Award this year. So I think he talked about this zero grading in his talk in last week. Yeah. So let me briefly explain the idea. So consider the loop statistics. You may think of, okay, so in a 1D, we have the particle can break around each other. So in 2D, one particle can break each other. But so in the 3D, maybe we can consider two loops which break each other. So let's consider I have a loop alpha and beta. First, I shrink this alpha a little bit and move inside this beta to the right-hand side. And then I enlarge this alpha again and come back to the original position. So you can see this gray arrow is the space-time trajectory of this alpha loop. But unfortunately, this two-loop gradient is always trivial. The reason is because let's consider this process. So its space-time process looks like this. So I first shrink the alpha and enlarge the alpha back to the original position. And we can smoothly deform this process from here to here. So because this loop can be created by out of nowhere, so you can see this process in the middle, it can be disconnected. When these two processes here disconnected, I can shrink this beta into a vanish. So, or you can move this beta away into other place. And this final process just this alpha gradient with vacuum. So this is some trivial process. Yeah. So this is the argument why the two-loop gradient process cannot give us any non-trivial index here. So that's the reason why they need to introduce a three-loop gradient. The only difference is beyond the loop, besides the loop alpha and beta, I need to insert the third loop here, gamma. It's linking with alpha and beta. The purpose of this gamma is to prevent the vanishing, the shrinking of this beta to some vanishing configuration. Yeah. So once we have this gamma loop, the beta cannot disappear anymore. So this three-loop gradient process can actually give you some non-trivial topological invariant. And besides this three-loop gradient, there's other paper by Peng and Xin. They actually consider other type of gradient process called fermionic gradient. So here the n corresponds to the loop excitation, and the gamma corresponds to the worldline of a particle. So in the 3D, the most naive gradient is you just move the particle around the loop, so they have a linking. So this gives you some particle loop gradient process. And let's discuss the more complicated one. So you have actually two loops here, Ni and Nj in the red and green color. And now you move the gamma across these two loops. So this is called a fermionic. So you can see if we just focus on the two colors, like the red and blue one, they are actually unlinked. Similarly for red and green, the red and green, they also don't link to each other. However, if we put three loops together, so they are actually linked. So you cannot move one loop far away. Yeah. So this is another loop gradient process they consider to study the topological case. Yeah. And for today's talk, so these are more like the mutual statistics. So we need to prepare different copy of loop or different copy of particle, and they consider the gradient between them. And today, I want to focus on the self-statistic. So only a single loop. How do we define some statistic of a single loop excitation? Okay, so let me try to give some definition for fermionic loop. So I want to notify you. So this is kind of a recent proposal. It only proposed in maybe 2021 or 2022. So they are still debating whether this is a good definition or not. But I will try to convince you why I think this makes sense. Okay, so okay, let me give you two properties of fermionic loop. The first one is by Vygotsky, R, and Hetting. So let's just consider our setting. So our setting is we have some membrane operator, let's call it UN. When I apply on some open surface, it will create a loop excitation on its boundary. So here I just show the example for this. If I apply this membrane operator on this disk, it creates a loop on its S1 boundary. Okay, so the first process is actually just a loop flipping. So let's consider I have a loop like this, and now I flip by pi rotation. So you can see kind of the orientation of this loop got reversed. But there's no orientation here. But it just help me to kind of to visualize. So consider loop here, you flip this one. But there's some subtlety. The loop here needs to have some 2 pi twist. Yeah. So we not only flip the loop, we flip the very specific loop. I call it a figure A loop. So you can see this is the ribbon diagram. Yeah. So let me go to the original slide. Yeah. So you can see this ribbon diagram is just the 2 pi twist of a ribbon. And now I'm actually trying to flip this loop excitation, so it has 2 pi twist. Yeah. So here, this is a spatial picture. It's some, for example, 3D space. I have some loop excitation, and now I just rotate this one. So you can see if this original loop has some arrow, like this red and blue arrow along this one. And if you do the pi rotation, so you can see originally it looked like, say, counterclockwise, and it's become clockwise. So this is the definition one. If we try to flip the loop, it gives a minus sign. And the second definition is in my paper with Boson, Boson. So we actually use a more abstract way to describe fermionic loop. So our definition is following. So consider I apply this membrane on some non-orientable surface. For example, if I apply this membrane operator on some Klein bottle, so this Klein bottle have some orientation defect. So we need to choose some orientation defect along this Klein bottle to define the Mobius field. So consider Mobius field, for example. So on the Mobius field, it has some orientation defect. So this can make sure the orientation on the left and right going through this defect that got reversed. And our definition for fermionic loop is this orientation defect is actually the worldline of fermion. So in other words, there's some hidden fermion excitation here. Yeah. Is this clear? Okay. So now I will try to show you the property 1 and property 2. They are actually connected to each other. So although they look quite different, but they actually give you they are actually describe the same anomaly. Okay, so let's consider the Mobius field as I described. So now I apply my membrane operator on this Mobius field. And according to my property 2, if this membrane operator creates a fermionic loop on this orientation defect, it has some fermion attached to this, the endpoint of this defect. And now, let me prepare 2 perpendicular Mobius fields. So consider this a blue one, it's this Mobius field. And now I rotate this blue one with 90 degrees, become this green one. So these 2 Mobius fields, they are become perpendicular. And now I try to glue a boundary. So I try to glue a boundary here and here. So these 2 boundaries, they become identified. And similarly, I glue the boundary this here and here, it's become identified. Yeah. So once this become identified, you can see this orientation defect. They actually have this figure 8 shape. So according to the property of fermion, we expect this orientation defect give you some minus sign. Okay. So the next question is become to this animation in the beginning. So let's just consider the two mobile strips. They are perpendicular to each other. And now I smoothly try to do the boundary. Yeah. Let me see it. Yeah. So actually, this manifold, this 2D closed manifold is a Klein bottle. There's some easy way to justify this. So consider this red one is one Mobius strip, and the blue one, first you move this bottom triangle to here. So you can see this blue one also become the Mobius strip. And now these two Mobius strips are glued along their boundary. And then you can ask what does this manifold correspond to. So you can see the top and boundary, they are identified in the same direction. But for the left and right boundary, they are identified in the reverse direction. So we can see this is a Klein bottle. Yeah. So, yeah. Yeah. That's a good question because the reason they cause is because the dimension we draw this diagram is too long. So actually they live in the 3 plus 1D. So in the 4D spacetime, the Klein bottle can, yeah. Because this is the spacetime picture. So actually in the 4D, they actually they don't intersect with each other. Yeah. The reason why we always think the Klein bottle must self-interact is because in the 3D, the dimension is too low. We have no way to embed the Klein bottle into 3D space. But in the 4D, there's no problem. We just embed in the 4D smoothly. Yeah, so there's some samples here. In this diagram, I avoid the framing. But the framing is also important, just like the particle case. We need to have some framing to say this is actually twisted ribbon or untwisted ribbon. But in the figure here, I sort of treating here. I don't draw the framing here, but framing is very important. So in the later slide, in the more technical description, I will introduce the framing again to how do we connect this thing into the W3, the Stiefel-Whitney text. Okay. Okay. So we already know when we try to glue these two mobile strips, it becomes a Klein bottle. Okay. So now let's try to go to my main point today. I try to propose a spin static theorem for loop. Okay. So let's just try to give the interpretation for Klein bottle. So consider this is the more standard point of view for Klein bottle. So you can see there's some nice picture. So you have some loop which self-intersect. And now if you cut it into two halves, each of them is actually a mobile strip. Yeah. You can spend time to do an experiment by yourself. So this is the standard point of view for the Klein bottle. And we can give this some physical interpretation. So at some negative time, it's a vacuum. I have no excitation at all. So at this time, I create two loop excitation. So for the right loop, it just go along the time. And for the left loop, it kind of have some flipping. So you can see along this one, it kind of flip the orientation and then annihilate with the other loop. Yeah. So we can interpret this Klein bottle as two loops with one loop flipping and then another two loop. On the other hand, from my previous argument of attaching two mobile strips, so this is nothing but just the orientation defect of the Klein bottle is the fermionic worldline. Yeah, so these two pictures, so this is just two different ways to visualize the Klein bottle, but they have the two different interpretations. This is the interpretation by Hikoski's paper. let's say when we try to flip the loop, it gives a minus sign. And this is our interpretation. It's like orientation defect is the fermionic worldline. Okay. Now, for the particle, we have some T-junction process to detect the particle statistics. For the loop, we also have some crazy steps to detect the loop statistics. So this is the 24 step I found by computer. So let's consider, let me explain. So let's consider the conversion like here. So we have a tetrahedra, 1, 2, 3, 4, and with the center point 0. And now I can apply some membrane upgrade. If I apply the membrane upgrade, says M14, M14 means I create a loop excitation around 0, 1, 4. Yeah. So similarly, I can apply some other membrane upgrade to create, for example, the loop excitation at 0, 3, 4. So let's consider this initial conversion. So this one. So for the outside edges, I draw the black line, and for the inside edge, I use the blue line for indication. So consider this one. When I apply M34, which means I attach the loop excitation 0, 3, 4 here. So when I apply M34 on this conversion, I actually become this conversion. So now I apply a sequence of geometry update. So let's go to the here. Now, so given this conversion, when we apply M14, M14 means I create another loop 0, 1, 4. So you can see 0, 1, 4. So when we apply the M14 on this conversion, let's go back to the original one. Yeah, I hope it's clear. Yeah, so it's a little small. Yeah, but you can see this go to there. So this is the closed loop conversion. But there's a very important difference. Notice that along this process, I always draw some black arrow to indicate the orientation of the loop. So initially, this black arrow is going from the vertex 4 to vertex 1 in this direction. And along this process, we always keep the single loop conversion. So we can see in this 24-step process, there's always a single loop around this tetrahedron. So we can keep track of this arrow. So for example, in the first few steps, the arrow doesn't change because the line is here. And for the next few steps, this black arrow here is always pointing to the same direction. So they are unchanged. So we can keep track of the orientation until here. But when we try to apply the last step and one for here, so you can see the orientation is going from here to here. And if we compare the orientation here, so according to here, the orientation is from 1 to 2. So this is vertex 1, this is vertex 2. And this is actually from 2 to 1. So they are reversed. So this process actually reverses the loop of orientation. Yeah. So this is the reason why this can detect this Klein bottle process. Yeah. So this process is found by computer. So there's another process by Stotsky, Hatching in the original paper. They have a longer step. It's a 36-step process. So I have shown that these two processes they are actually equivalent, but maybe our method is kind of more optimal compared to their method. So we use a slightly different approach. In their paper, their requirement is they try to generate a sequence such that all dynamical phase cancel out. Just like T-junction process, if a particle moves from one location to the other, you must have the reverse orientation, reverse process to go from this location to the original location. Make sure that all dynamical phase they cancel. And similarly, they try to make this congruent for the loop excitation, and they find some statistics that. And for our ongoing project, my student and I will use another method. Due to the time limit, I cannot discuss this detail, but we use a more computational approach. Basically, we try to solve the Smith-Normal form for certain locally constraints, so we can generate this 24-step sequence. That's a good question. I have no idea. So maybe it's kind of 3 factorial, 4 factorial, 5 factorial. I'm not sure actually. So the next project I plan to do is actually with Chen. We try to work for the 4 plus 1D for the membrane excitation. So maybe we can kind of define what the fermionic membrane. Yeah, but we expect the state may go exponentially. I have no idea. Yeah. The list number 24, I'm not sure whether this is a minimum. So we use some optimization algorithm, but it's not guaranteed it's the smallest. But yeah. Right. Yeah, that's a good question. Yeah, I haven't paid too much attention for this number because they actually correspond to the same invariant. Yeah. Maybe it's more important for practical purpose when you try to detect whether on your experimentation, whether this is fermionic loop or bosonic, you want to have a fewer steps. But at this point, they are actually equivalent. Okay. Now let's go to some lattice model to describe our definition for particle and loop. So let me just give the easiest example. It's called 3 plus 1D torical. So the torical, it has a charge and loop. So in this case, the standard torical is bosonic charge and bosonic loop. So let's write down the action for a torical. It's very simple. It's just like an ATB. It's sort of like a Chen-Simon, but it's like a Chen-Simon in the 3 plus 1D version. So A corresponds to some one form, and B corresponds to 2 forms. When we try to write down the equation of motion, it's basically a dA equals 0 and dB equals 0. Yeah. So this kind of equation of motion can be defined on the lattice Hamiltonian. Yeah, so usually we have this is called the star term. The star term corresponds to this dB equals 0. So you can think of in the dual lattice, the star term is actually dual to a sphere. So on the sphere, the product of x equal to 1. And similarly, for the dA equal to 0, dA just means the boundary of a square. So it's like product of z around this square equal to 1. So this is the standard torical Hamiltonian, and we can actually study its excitation. So for example, the z string here will violate this star term. So this creates some particle excitation. It's called E charge. And when you apply the membrane upright, the product of x along this vertical line, and you can see it only violates the placate term around its boundary. So you can see if I put in z placate here, and the single z here will be anti-commute by this Pauli x. So this x membrane upright creates a loop around its boundary. And since the E charge is purely Pauli z and the loop is purely Pauli x, they don't have any fermionic behavior. When you deform, it's either particle or loop, they always commute with each other. So this is bosonic charge and bosonic. Okay, so previously I have sort of demonstrated for the fermion particle, it's actually the worldline is no longer dA equal to, sorry. So for the boson, it's dA equal to 0, but for fermion, it's dA equal to W2. The second Stiefel-Whitney test tell you when the fermion will give you some minus sign. So it's very natural to generalize this definition to the loop. When we try to deform a loop along some space-time process, the bosonic loop give you dB equal to 0, like this term. But for fermionic loop, it becomes dB equal to W3. So we need to ask what's the value of W3 in the list manifold, the volume be enclosed by this space worksheet. So this definition is first proposed by Ryan Sango almost 10 years ago. But in his paper, he just barely say we can generalize the W2 to W3, but it doesn't quite provide any concrete example or like a lattice description. Yeah. Okay, so in the last 10 minutes, my talk will become a little bit technical. It's called gravitational anomalies. I will explain the rough idea. Yeah. So first, this action is the C plus 1D torical I described to you. And now I try to twist the theory. So which means I try to add more terms into my action. So this will change the statistics of the particle. How do I see that? So given this action, we can still try to solve the equation of motion. When we try to integrate our A, this gives you dB equal to 0. When we try to integrate our B, this actually gives you dA equal to W2. So which means in this model, the particle is fermionic, the loop is bosonic. Okay, so to actually detect this fermionic statistics, we need to couple the fermionic worldline into some background field. Say we couple this little a is the fermionic worldline into some capital A3. If we try to make this background field become dynamical, it has some problem. This is because it has some anomaly. So I'm going to show you. If I try to apply this gauge information, so which means my background gauge field is trained by some coboundary, and I need to train this B by some beta correspondingly by some 2%. And you can see if I only have these 3 terms, it's not enough. So this 3 terms is not gauge invariant under this gauge information. We need to cover to some higher dimensional term. So notice it's N4, it's my spacetime, and we need to introduce the 5-dimensional manifold like X5 such that N4 is boundary. We need to introduce this extra term to compensate the anomaly of this in this 3 plus 1D theory. Yeah, so basically the physical interpretation is we cannot get the fermion. So the fermion cannot be condensed because the fermion is an anomaly. So this anomaly will show up in a 1 higher dimension. So this is quite similar to the so-called like a generalized symmetry, the idea of sensitivity. The anomaly is captured by the topological order in 1 higher dimension. Okay, so let me ask, what's the physical meaning of this extra term? Yeah. So first, we can use some knowledge about the algebraic topology. When we have some car product between W2 and some cocycle, we use the U formula to make it become some general square, and the general square become the AC top 1 AC. Now this is just some technical detail, but I want to show you the geometrical interpretation. So let me just go to one lower dimension. So let's go back to 3 plus 1D and see what does this A2 plus A2 mean. So consider I have the A2 here. So you can think of A2 is some point-correct dual of fermion worldline, and this A2 prime is its framing. Yeah. And now let's try to change the framing. Say this is on twist 1, and this is the twisting 1. So consider we have some movie here. Let's go from here to here. So at a certain point, this purple framing must touch the red line to have this twisty framing. Yeah. And this touching point is captured by this integral. Yeah. So in other words, this anomaly in a higher dimension actually give you the counting. It counts the number of times you change your framing. For each time you change your framing, you have some minus sign by this topological type. Yeah. So this is a more technical but more mathematical rigorous way to justify the connection between the second Stiefel-Whitney test and the twisting of framing. Yeah. So we can just try to write down a Hamiltonian, try to write down this fermionic toric into Hamiltonian level. So in the bosonic case, we have the starten and some placation. But in the fermionic toric, we sort of need to modify this placation into some a little bit complicated way. But this is just still some commuting projector, exactly solvable, Pauli stabilized code in 3D. So you can still try to write down the particle excitation and loop excitation. Yeah. In the original case, the particle excitation is just some Pauli Z string. But for this fermionic toric, its particle excitation is a little more complicated. It's a product of Z times X. Yeah. But you can convince yourself the particle excitation in this model is actually fermionic. Okay, so due to the time constraint, I will try to avoid the computation for the loop, but it just follow the same strategy. We first add some time to modify the equation of motion to make sure it becomes a Fermionic loop, and we try to gauge this loop. However, since this loop has some anomaly, it must cover to some higher dimensional terms to compensate the anomaly for this gauge information. Yeah. So we can draw a very similar diagram. It's too complicated. I think I don't have the time to explain this well, but I just try to emphasize the W3 car B2 also has some nice interpretation of the 3D framing, but it's the 3D framing around the orientation defect of the Klein battle. Yeah. So we have some mathematical foundation to connect the W3 anomaly and the Klein battle project I described before. But let me make a comment here. So this may be related to Chen research. So I know from Steele Johnson 3, they study the two categories. So they actually did from using the language of two categories, they can define the Klein battle invariant. Yeah. So we believe the Klein battle invariant from the two category point of view should be identified with this W3 anomaly in some way. But I have no way to make this connection rigorous. So far, the only evidence is both of us use the Klein battle, and both of us define some topological invariant for worksheet of loop. Yeah. Okay. So in the last two slides, let me give you some example of Fermionic loop. Yeah. So actually, in the standard Stiefel-Whitney toric, they already exist some Fermionic loop. The upper level is look like this. So when we write a B2 corresponds to the N loop, is a Pauli X. And when we try to write down the B2 plus A1 plus A1, it's just also some membrane excitation, but this A1 plus A1 becomes some consolidate gate on this space. So when you try to plug this operator into this definition of this 24 steps, it gives you a -1. Yeah. So it's kind of hidden inside the standard toric. So in the standard toric, there's already some excitation correspond to Fermionic loop. Okay, so in the next 2 minutes, let me just quickly summarize my talk. So first, I review the spin statistics theorem for particle. It's just nothing but the interpretation of this twisty ribbon. So the two different interpretations correspond to spin and the statistics. And now we generalize this picture for the loop excitation. So given the Klein battle, and more importantly, the Klein battle with some 3D framing, but the framing I didn't draw here. So we also have two ways to visualize the Klein battle. One is about the loop flipping, and the other one is about the orientation reversing defect of the Klein battle become a fermionic worldline. So we have also two different interpretations, and it's kind of generalized version of this one. And we argue that the definition for Fermionic loop, so for fermion and Fermionic loop, come from the second and third Stiefel-Whitney test. Yeah, and yeah, so I haven't gone through these two, but let me just define my future direction. The first one is definitely straightforward. We need to go to higher dimension. So how do we define membrane excitation is fermionic or not. I conject it's related to the force Stiefel-Whitney. But this requires much more computational power, and in the 4+1D, it's not easy for humans to actually visualize what's going on here. So I cannot image how do we flip the membrane or do anything there. Yeah, but I think for the computer, my program can actually drive to higher dimension easily. Just require much more computational resource. Okay, so my talk will end here. Thank you for your attention.
Thank you for the next talk. So my question is like, so it seems you defined the spin of some loop operator in your any. So my question is it possible to use the same method to figure out the self-repeating of any type of loops?
Yeah. That's a very good question. So this is actually ongoing project. So this is related to how I find this process. So from Vygotsky's process, they already have the knowledge that we need to flip a loop. So they write a program to find a way how do we flip this loop nicely to make sure everything cancels out. But from my approach, I don't need this assumption. So I just start with some basic conditions. Say the log unitary operator, they have some locality constant. So for example, I have some membrane operator here, and membrane operator there, they need to compute. And this is my condition. So I just try to input all conditions into my computer. And then I compute the Smith normal form. The Smith normal form can tell you which relation is the most important one. So it will basically just diagonalize a very huge matrix. And after the Smith normal form, the diagonal will have some number. For example, 2, 2, 1, 1, 0, 0. And for this 2 means certain operator says. So first, so the Smith normal form can give you some operator O squared equal to 1. For example, this gives this concept. So this gives you O equal to plus minus 1. So this can teach us there's some Z2 index in the system. For example, this O can be this process, can be T-junction process, can be the loop particle braiding. Yeah, so this is a loop, and you have some particle E loop. Yeah. So the idea is very simple. For any dimensional manifold or any context, you just input all locality conditions, and you just compute the Hamiltonian form to give you all particles. Say it give you O1 equal to 1, give you O2 false equal to 1, give you O3 2 equal to 1. So you know this O1, O2, O3 will give you some physical process. So in this case, I only input the membrane operator. So this giving my O1 is actually this loop splitting. However, if I input both membrane operator and a string operator for particle, this can give you the membrane, the loop, this mu, also can give you the T-junction of particle, and this also it can also give you the mutual braiding between the particle and loop. Yeah, so I think our method is much more powerful. So we don't actually have any presumption of we need to look for like this loop splitting. We just try to insert all of our knowledge about this operator, and the computer can generate all possible topological index.
Okay, sounds very powerful. Thanks.
The existence of the fermionic loop operators actually depends on the non-vanishing of gravitational anomalies, as you mentioned. Then I have a reverse question. So if we know there is a gravitational anomaly, then can we always derive or actually show that there always exists such fermionic loop operator in your theory, like including quantum field theory and also condensed matters?
You mean finding an example of?
Yeah. I mean, if we know that there exists such gravitational anomalies, then can we just conclude that there has to exist such fermionic loop operators in the system? in some.
Yeah, that's a good point. I think answer is yes. So basically, the way we detect whether this particle, this loop is anomalous or not, we just couple to some background field and make it dynamic. So we try to condense this loop using category method. So when we try to condense the fermion, it's not doable because it has some anomaly, and this anomaly will become a W2 in the 100. So in principle, I believe all possible statistics can come from this way. You just try to condense or try to gauge this higher form symmetry. If it is not gaugeable, it will give you some gravitational anomaly in the higher dimension, and it can give you a way to define new statistics. Yeah. So actually for 3D, for loop, it only has W3, but for 1 high dimension, we have W4, we have the P1, the Pontryagin test. I think the Pontryagin test can also give you another statistic for membrane excitation. So it has a much richer variety.
Yes.
Mentioned in the maybe the last slides that already in the toric code you can see that -1.
Yes.
You mean this in the usual toric code?
Yeah, it's in the usual toric code, but it's kind of the fake example because this loop is just some charge decoration on the end loop. So basically you have an end loop and you decorate on each charge. And with some proper decoration, you can make this loop more sort of like a fermionic, give you some -1. Yeah.
One question? Okay, if not, let's speak again.
Yeah, thank you.